going to start it from here. Okay, so when we're solving trig equations, we are trying to describe the angle do I get sine to be 1/2? Well, on our unit circle, remember that sine is equal to the y-coordinate on the unit circle. So where do we see a positive 1/2 for the y-coordinate? At pi over 6, and then again at 5 pi over 6. So pi over 6 are two solutions that we get directly from the unit circle. Okay, and that'll always be where we start. Okay, what values or what angles are we seeing those coordinates show up on the unit circle? Take a unit circle and do multiple revolutions around it. So remember back when we first did trig, one of the first things we talked about was coterminal angles. And that means if I rotate to pi over 6 and then I do a full rotation, so that would be pi over 6 plus a rotation, which is 2 pi. So another solution here is pi over 6 plus 2 pi. And then we get another one if we rotated once and even twice. So pi over 6 plus 4 pi. So there are actually infinitely many solutions we can get multiple times. Now another way to visualize that is to take the graph of sine of x. And know that every equation that you solve, there's a graph that represents it. So sine of x, that's what we see here, that little squiggly graph. Sine of y being 1/2. Well, our solution is anytime these two things intersect. And we easily see those 2 points where they intersect at pi over 6 and 5 pi over 6, which we got from our unit circle. But then if we add 2 pi, this is where we get these other two solutions of 13 pi over 6 and 17 pi over 6. So and positive infinity, so there are actually infinitely many solutions. So our task today is going to be, how do we describe all of the solutions to a given equation? And it's going to look like this. Any multiple of 2 pi can be added to these values. Thus, all solutions of sine of x equals 1/2 are given by the following equations. X equaling pi over 6 plus, this is 2n pi. I'm going to write it as 2 pi n when we go through our own examples. How many other times can we rotate around the unit circle? So let's make a separate note here that n is an integer. And an integer meaning whole number. We can obtain new angles that make this equation true. And let's just do that real quick. We'll do that a little bit more next when we come back from break. But let me just show you what I mean by that n value. So if n is 0, meaning we're not adding pi over 6. So those same two solutions we found from the unit circle. Now we would get two more solutions by letting n equals 1 and subbing 1 into this equation for n. So that's x equals just 2 pi, and then 5 pi over 6 plus 2 pi. Well, we can get common denominators here and add these together. So this becomes pi over 6. 2 pi is equal to 12 pi over 6. And then 5 pi over 6 plus 12 pi over 6. And so that makes this 13 pi over 6. And then 5 plus 12 is 17 pi over 6. And so there are two more solutions that we get after adding 2 pi. And we can get more by letting n equals 2, n equals -1. Any value of n will change the solutions we get. All right, questions so far? Put the phone away. Thank you. Anything you mentioned that door for me? Thank you. All right, we're all good here? Okay, well, let's go through an example from the start, because I know there's lots of kind of extra words that we added in there. Gavin, okay. Nothing. I started a sentence and I cut myself off. Okay. You might have to lift it up with your hand. Oh, there you go. Thank you. Okay. So, again, one thing I've talked about for those of you that have been with me is when we see equations, or just as we approach math, I want us to not get so caught up in memorizing steps and being more conceptual. And what I mean by that is when you look at an equation, before you even start, you should think about what is your answer going to represent. Well, all these x values are any angles, okay? So our solutions here are angles. So we're trying to figure out at what angles does sine equal √3/2. So if I ask what do your solutions represent, you should all say angles. Okay, we're trying to describe the angles here. Now we're going to start by finding these angles just on our unit circle. So we're going to first search within 0 to 2 pi, where we see the y coordinate to be √3/2. So let's grab that unit circle. And sine is the y coordinate. And we get y to be √3/2 at pi/3, and then again at 2 pi/3. So those two solutions to start are x equals pi/3, and then x equals 2 pi/3. And then from here, we're basically adding the period of the function. So that's the last thing to consider. And remember that the period for sine and cosine is 2 pi, but the period for tangent is different. So with the period being 2 pi, I'm going to add 2 pi n onto these solutions. And it's these equations that describe all the solutions to this equation. Yeah, go ahead. Okay, and that's all we're working on today, is finding ways that we can write these equations that represent the full solution set. All right, why don't you all go ahead and do cosine of x equals 1/2. We'll save tangent to do all together, but why don't you all go ahead and do cosine, and we'll go over that from there. A couple minutes to work through that. Take it. There's no Levi in here, right? Levi, okay. I gotcha. Sorry, Levi. And then Walker, right? Walker, gotcha. And Nina, right? Nina. Drew, right? If you're watching online, sorry, I had recording going during the idle time, so there's extra time in the video. For all of you, over 3 plus 2 pi n, and then 5 pi over 3 plus 2 pi n. And that's because cosine is positive in quadrants 1, and then again in quadrants 4. Okay, and that's really what we want to pay attention to. Where are those given trig functions? Unfreeze. Yeah, BK, what you got?
Why are you adding plus 2 pi n?
Because that accounts for extra rotation, so I'm adding an extra 2 pi to get back to that. So we're accounting for multiple revolutions around the unit circle. Okay, so we'll always add some values because the graph, remember the graph extends from negative infinity to positive infinity. So there are infinitely many solutions. So the 2 pi n is a way cosine. But with tangent, it'll be a little bit different because the period's different with tangent. Other questions here? Okay, well, let's talk about tangents. And tangent's a little bit trickier because and look for root 3. We have to think about if we take y divided by x, which one of them is going to reduce down to be just simply root 3. Well, one thing I know for sure is it's not pi over 4, right? Because at pi over 4, both is 3. So that tells me it's probably either, well, tangent's positive in quadrant 1, so either pi over 6 or pi over 3. For some of you, you might be able to do that math, the y divided by x in your head, and say, I think it's pi over 6. And I'm going to do y divided by x and see what that gives me. So tangent of pi over 6 is equal to y over x. And at pi over 6, the y coordinate is 1/2. Two over root 3. Well, the 2's divide out, and I get 1 over root 3. And we don't like the square root in the denominator, so I multiply it by root 3 over root 3, which is root 3 over 3. And that is basically confirming that our solution is not pi over 6. So I'm then thinking it's more than likely pi over 3. Let's just check it real quick and see what happens when we do tangent of pi over 3. So now y over x is root 3 over 1, and the 2's divide out, and I get just root 3. So our angle that works here is pi over 3. So x equals pi over 3. But now, this is where we need to consider the period. And because the period's pi, we don't need to find a second solution on the unit circle. On the unit circle, and we kind of talked about this when we graphed tangent, once we go from quadrant 1 to quadrant 2, we've solution and then add pi n to both sides. And so we don't have that kind of second solution that we get like we do with sine and cosine. All right, questions here? We're changing the period, so we have to do a little bit of extra work on top of all these, what we've been doing thus far. Different. Sine of 2x, if we were to graph that, the period of this graph has changed. It went from 2 pi to now 2 pi over b. So the period here is 2 pi over 2. Or even like a phase shift. So if we had a value added or subtracted in the parentheses, we're basically going to ignore what's in the parentheses to start. And so the first thing we're going to do is actually take sine of x and describe when it equals root 3 over 2. And we're going to ignore the 2. X equals pi over 3 plus 2 pi n, and then x equals 2 pi over 3 plus 2 pi n. That describe the solutions to regular sine to come up with our solutions for sine of 2x. And so basically we're going to place all of these x's here with 2x and then solve those equations from there. Our task is to get x by itself, which I can do by dividing everything by 2. And we're going to have some simplifying that we need to do from there. So we divided by 2 is just pi n. And then x equals, that'd be 2 pi over 6. And that's going to need to reduce down, plus pi n, so x equals pi over 3. The solutions to sine of 2x equals root 3 over 2. So because the period changed, it changed the values that we originally get, root 3 over 2, and then for us to get our next set of solutions, all right, questions here? Okay, so just real quickly, I'm going to have you all describe the solutions to cosine of 2x equals root 2 over 2. Take about 2 minutes to get through that, and that'll bring us right to the end of class. So our solutions to regular cosine of x are pi over 4 plus 2 pi n, and then 7 pi . Okay, so after we get these solutions, now I'm going to replace the x with 2x, and then everything needs to get divided by 2, making our final solutions to sine, our cosine being 2x changes because of the period change with that too. Right, and then the last one with tangents. So now here with tangent, pi n, but now it's x divided by 2, so everything needs to get multiplied by 2, making our final solution set 2 pi over 3 plus 2 pi n. Okay, tomorrow we will get more practice.